We fantastic. It's really cool. Yep. 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 Like a minute. I mean, give it a try.
Okay, good morning, everybody. Welcome to the 2018 Sensor CDT Team Challenge presentation. The 10 students of this cohort worked for about 3 months on this project. We gave them the initial brief, a very broad topic, and then it was all over to them to actually come up with the implementation, and we'll see what they've achieved in the last 3 months, approximately.
Okay.
Hand over to Francesca and enjoy the presentation.
So, first of all, thank you very much, everyone, for coming today. And can you all hear me? Good. So, as Oliver just said, we're a team of 10 students doing a 10-week project, which has culminated in this, which we'd like to present to you today. I'm going to call it CAM-like sensor. So, motivation, just to give you an idea of why we decided on the project that we decided on. So we, as I said, we're 10 students, and we got a team challenge brief, which was do a citizen science sensor project. Now, I assume you all know what it means to do something with a sensor, but what citizen science really means is that we try to get people who are not necessarily scientists involved in our project to help us collect data with many hands make light work, but also to show them that science is really fun and interesting, and that some of the issues that science can engage with are very important. Now, so we got thinking, if we're going to do a citizen science project in Cambridge, where we're based, how do we connect with people? What do people in Cambridge really care about? And looking around, we fairly quickly arrived at bikes. So we may have seen headlines similar to this at some point. Cambridge, also on the City Council website, calls itself the UK cycling capital. Nowhere else there are more people who cycle once a week or who commute to work by bike, in the UK at least. So we thought, cyclists, that's an interesting idea. A bike goes lots of places, so if we could put a sensor on a bike, we could potentially measure interesting things. So then we had to think, like, what is important to a cyclist? How do you get a cyclist to stick your sensor on their bike and measure things? And we had to think, well, obviously, if you're a cyclist, you're on the road, and if you are a cyclist yourself, you probably know it's not very nice to cycle on bumpy roads. So if we could quantify that and identify problem areas, that would be interesting. But also, a cyclist is in traffic, and when you're in traffic, you're exposed to the exhaust from motorized vehicles. That is not necessarily very pleasant. And we also thought about a citizen science project where we collect lots of data could really benefit in that kind of area. It's like, this is the map of all the continuous monitoring stations for particulate matter, which is a form of air pollution, which we'll get to later, in the Cambridge City Centre. So that's only 5 points where you're doing measurements every hour. We thought if you stick a sensor on a bike and go everywhere, because those things are mobile, we could cover the entire city and get a lot more detailed data that could be really interesting. So that's what we set out to do, and what we'd like to tell you more about today. So without further ado, let's get to the technical things. Thank you.
So now let me introduce you to the sensor hub and to the hardware kind of side of things. I would like to start with an evolution of our prototypes. And those of you who follow us on Instagram or Twitter might have seen this one. This is the very first prototype we had. It is based on an Arduino microcontroller. It already had GPS geolocation, an accelerometer, and wireless transmission using the Sigfox network. So for this one, we came up with a very neat case design, I think, because this tube design fits a regular bottle cage. So you can put it on any bike. And this sensor design actually went to Paris with Peter. We live streamed this on our homepage. You might have followed this. So then we moved on because the first version didn't have air quality monitoring, and we had to duct tape the air quality sensor to the bike, and it was not very nice. So in terms of for getting a measure of air quality, we decided for particulate matter. This particular sensor measures PM 2.5 and 10 micrometer particles in the air. We hear about that later, actually. But yeah, this design was forcing us, or the size of the particulate matter sensor was forcing us to choose a bigger case design. We also included SD card logging because we realized we're getting tons of data. And what we then came up with is a very low-cost solution, but a very pragmatic one. We used the standard pipette tip boxes we had in the lab. The advantage is they have a transparent lid, so we could see all the status LEDs. We drilled holes for the SD card slot, for an air tube inlet, for the GPS antenna, and there were a lot of cables in there. It looks quite nice. It even went punting with us. And I think a handful of sensors are actually in distribution right now with this case design. But this is not where the journey ends. Our vision was to do a truly modular design of the sensor hub. So we decided to do our own printed circuit board, a PCB, that's modular. So even kids or the citizens themselves can build it. Just buy all the components or get a kit from us, stick it on there, flash the code, and there you go. So we actually only received this week. So now I would like to guide you through the components we have. First of all, we have the heart of the whole system, which is an STM32 microcontroller. It's commonly called Black Pill. We chose it because it's very low cost. It only costs less than £2. It has a large number of communication pins and a lot of memory, 128 kilobits, so it could fit our code. The next bit is the GPS module. We chose the Neo 6M module. It features a very short cold start time, which we need. As you start cycling, you want to have GPS right away. It has a very robust antenna that doesn't interfere with our electronics because we have everything very close by and a lot of cables in there, as you can see. So there's low interference. The next bit is the accelerometer. It also features a gyroscope, so that allows us to measure the road quality and bumpy roads. We get spikes in the accelerometer data. The next thing is the particulate matter sensor, which is mounted below this PCB. We actually oriented the PCB side towards this particulate matter sensor. So it's basically a very flat and square thing now. Then we have the SD card still, which logs everything. It makes it very bulletproof. And a key feature is the LoRa transmission. LoRa stands for Low Power Long Range Radio. It has about a 10-kilometer range. It's a very novel technology because now we tend to connect everything via IoT wireless. So rather than Bluetooth or Wi-Fi or SIM cards, GSM network, we don't need a subscription here. We have a very long range, and it works right away. So of course we have to power the device. So we use a lithium polymer battery for that, 1200 milliampere hours, 3.7 volts. Our components use different voltages. So most of them run on a very low power basis. So for example, the MCU, the accelerometer, and the wireless transmission, they all run on 3.3 volts, so we need to step down this 3.7 volts. But also, there's a more power-hungry component in there, which is the particulate matter sensor, so we need to step up to 5 volts as well, just to mention this. And a feature that I'm a bit proud of is the LED button, because we had many problems in Paris, for example, with this black tube, that you had to open the whole device before you could see what's going on. Is it on? Is it logging? Is the GPS actually catching reception? And this can act as a status LED as well. It can blink. We can do many things with it. It all comes together to this case vision we have. We had a couple of requirements to the case. It should be waterproof, because as you start cycling, weather conditions might change. But it also needs some air ventilation. This is hard to combine, but with the tube, we managed to find a way that kind of works. We also need a fixed orientation. It needs to be perpendicular to motion, because we don't want the airstream from the cycle wind to go right into the particulate matter sensor, so it needs to face the road. The tube faces the road for overtaking cars to suck in the particulate matter. Also, the sensor tends to aggregate over time the particles in there. So the data sheet says you should have it horizontally. So we decided to mount it under the seat post, for example, where it's always horizontally. Also, it should be detachable, because you might want to take your sensor off the bike inside to charge the battery. And it needs to be very universal. So every bike is different, and we want to fit it on every bike. And one last thing, many people ask us, how will the sensor case look like? Will it look cool? And yeah, it should be good looking. So this is what we came up with in the end. It's a wooden case. We laser cut it. And we even have a transparent lid now, and the button. I hope it works. I might hand this around. You can attach it to your bike with these cable ties. We can try that after the presentation. But now I would like to hand over to Luca, who's talking about particulate matter.
Okay, so as Francesco said in the beginning, our main purpose is to measure air quality dynamically on the road using cycles. So as you can guess, the sensor for air quality is a vital part of the sensor of the final device section. So first off, air quality can be bad for many different reasons, but on roads, the main reason why air quality is bad is traffic, so cars. As you can see, cars can emit a very nice variety of pollutants. So nitrogen oxides, carbon oxides, volatile organic compounds, and particulate matter. So potentially you can measure all of them using existing sensors, but given the time and money constraints that we had, we decided to focus on one, which in our case was particulate matter. So particulate matter is a very fancy name for meaning fine dust that we breathe. It's suspended in the air all the time. It's so small you cannot even see it, but it's there. The biggest particles are about 1/3 of the diameter of a hair, and they're small enough for our body to take them up easily, but they're not big enough for our body to expel them easily. So they're in a very critical range, and they're very bad for us. So there is the reason number one why we decided to go for particulate matter sensing. Reason number two is that some pollutants in Cambridge, like nitrogen oxides, their levels are so low that you cannot really detect them unless you have very top-notch sensors. And we want to keep everything very low cost, because we want people, like all the cities, to be able to build and get our sensor. So we didn't build the PM sensor ourselves, we just got one. So we got this SDS-011 one, which measures PM 2.5 and PM 10. So in terms of micrograms per cubic meter. So it's fairly easy. Air goes in through the inlet, then there is a fan that the fan sucks the air in and then there is the laser and the photodiode, and by dynamic light scattering, we get the amount of PM2.5 and PM10. So it works in the -10, 60-degree range, which is fine for us. And we put it in a clean room where we knew that PM10 and PM2.5 values were 0, and we got 0 out of it. So there was no baseline correction to be made, but obviously we wanted to know if the sensor was giving values that were real or not really. So we wanted to calibrate the sensor. So for doing it, we put the sensor on top of an official monitoring station here in Cambridge. I don't know if you can see it, it's up there, here. And we left it there for a few hours. And this is what we got out of it. So our sensor, this one, underestimates the values. But it's good enough for understanding when PM10 is going up or when it's going down. So we decided to not really go for sensing particulate matter in absolute terms. So we don't really care to know if on a particular road at a particular time PM10 level is 2.5 or 17.65 or whatever. We just want to know what roads are nicer to cycle on and which roads are not so nice to cycle on. So from now on, everything we show is relative to Cambridge. So low levels are low for Cambridge and high levels are high for Cambridge. So what we did next, this is a bit of a spoiler of what's coming next. So all of us got a sensor and we went cycling through Cambridge, like all of us at the same time, to build dynamic air pollution maps of the city. So obviously there is a lot of stuff, of computational stuff going on. We're going from here to here. And Charles is our expert of data analysis, so he's going to talk to us about it.
First of all, I'll talk about how we're handling the data. So ideally, we have all the data coming through OL1, and it's automatically being indexed into a MariaDB database. And we are logging, obviously, all the sensor output, in addition to also unique identifiers for the sensor unit that a particular person has. And here you see an example table of part of the payload from one unit, the time of retrieval, the ID, and also the GPS coordinates. We have a few other ways we can also provide the possibility of storing the data. So if people prefer working with SD card, having the data files locally, but still want to visualize them, there's this upload tool we made. This particular one is open access, and each file that's being uploaded is anonymized. So the file name is transformed via a hash function, and you're redirected as soon as you upload here to the visualization page that I'll show you in a minute. First of all, we also have a file manager. We intend to make it open such that users can have their own login. For now, this is an internal tool, so we can see all the files that come through the open access. We can also upload files through this manager ourselves. And the buttons over here do a bunch of different things. We can plot the data in 2 different ways, one of which we'll see in just a second. So for the visualization, we've chosen to go with Google Maps API. We could as well have used OpenStreetMap. Google Maps API is very efficient, as well as quite easy to use. Before feeding it to the API, we pre-process it in a couple of different ways, some of which can be toggled on and off. So first of all, we interpolate. There will be a certain spread in the data when we acquire it. We want it to be very spatially uniform, so we have every 2 meters an interpolated point, giving us a very continuous trail. We can also smooth it, of course, and do various things with it. And in the end, we draw it with rectangles in the Google Maps API. So we can very precisely give a width and a color. We have experimented also with heat maps, but we chose to actually use this approach instead. It's more accurate, less misleading. So here is one example of the map functionality that you have through Google Maps. You have all the regular stuff as you would expect. satellite images, panning, zooming. So it's easier for users to navigate, get a sense of where they are. We also implemented different color maps. We had one user already who had our color blindness and essentially lacking the capability of distinguishing red and green. So just using a different color map like this is very useful for some users. Then we can also show different sensor output this way. For now, we have been looking at PM10. Here is a toggle for PM2.5. We imagine also having other kinds of sensor output. Could be accelerometer data. Could be that we want to essentially try to estimate road quality at some point, and that could be just another toggle for this. So here is an example of how the output process works. You can drag and drop a data file. It's being uploaded. You can see in the file manager, after refreshing it, file turns up, and you can use the plotting buttons in the file manager also to get the same plot as we see on the left-hand side. So it's very easy to use. Finally, a little bit about data analysis. This problem that Luca, he briefly mentioned, is that how can we combine multiple tracks of data? We expect to have many users collecting data at the same time. So we have to find a way to aggregate the data, combine it. And on the left-hand side here, we see 50 trails, many of which are overlapping. And there are many ways that you could aggregate them. One simple way that is intuitive and works well is nearest neighbor approach. So basically, we make a grid throughout the city. At every node, you average the nearest data points that have been acquired, and you make a prediction for that point based on a weighted sum. By that approach, you could turn this map of 50 trails into one singular network of roads, where all the data points have been averaged in this way. Finally, you could use the same approach to do something a little bit more speculative. You could try to predict points that have not been covered at all. By training this model using the acquired data and using it to infer roads that are in between two other roads that have been covered, for instance. Or the case where it probably goes wrong is if you try to predict inside a park or something and you only have data points around it. In that case, this would not be very useful, but otherwise it could be. For now, that's it about the data analysis. I'll hand it over to the outreach group.
Thank you, Charles. So as you just learned, a major part of this project was not only to build this very cool sensor, but also to reach out to the Cambridge people and make them contribute to our project. So our goal was to involve the public into our project and raise their awareness of environmental issues. So we were hoping by distributing our sensor to the public and equipping them with them that we hand them the tools to make a difference in their local environment and community. Our strategies to reach the public were quite diverse. So we knew that people of different ages and backgrounds have different media consumption patterns. So on the one side, we were aiming for traditional media. We were featured in various newspapers and bulletins around Cambridge. But we also gave interviews to the local radio station, Cambridge 105, and an interview to the TV broadcaster, that's Cambridge TV. We also wanted to aim at the younger generation, so we set up Twitter, Facebook, and Instagram pages, also a web page, which you could constantly follow and keep updated with us. So as you reach the people, you always have to keep them involved in the project. So we hosted a series of events, first of which was a makeathon. In this event, we try to target like experts from various backgrounds to help us tackle challenges that were associated with the project. So as we successfully reached out to the maker community of today, we also wanted to reach out to the maker community of tomorrow. So we hosted an event at the Center for Computing History, which was a children's workshop. And in this workshop, we taught the children about basic electronics and also the like the basics of air pollution and the risks associated with it. The next we gave a little solder class and helped them build their very own light version of the camera sensor that you can see here. Is this good? No. Oops. Jesus Christ. Okay. In the lower right corner. And then finally, the children, together with their parents, cycled around the museum and collected their very own data and uploaded it to our system. So handing sensors to children is a very nice thing, but for the large scale collection of data, it's not very useful. So by now, we started distributing sensors to the wider Cambridge public. It's been 5 prototypes so far, with more to come. And so what we're doing is we're running sort of a lending scheme that people can have the sensors for a couple of weeks, and then just give them back to us for maintenance, and they upload the data and analyze them there on their own. So I hand it back to Francesca for final remarks. Thank you.
So that was an overview of everything that we've done so far, but of course we'd also like to tell you what we still plan to do, which is quite a few things. So as Chris was mentioning, first things first is to upskill distribution, get the prototypes out there and start collecting data. We have enough components to build around 50 devices, 5 are running, and we would like to distribute the other 45 as well, and really over the coming few months get a lot of data. That will help us to really map Cambridge at different times of day, rush hour versus quiet afternoon on Sunday. And also for the accelerometer data, if we get a large training set, we should be able to start the machine learning process for real and get exciting information. And then to ensure that, so the idea is to give sensors to lots of different volunteers who all map their own commutes and ensure that we build up a map of the routes that matter to residents. And also to ensure that we're very, very thorough. We're partnering up with the eco-friendly last mile delivery company Zenify, who use bikes for parcel delivery, and they'll stick around 5 or so sensors on their bikes for a couple of weeks, and because they will get used very intensively, so we should get a lot of data out of that. And then finally, also, we will be taking a break of a couple of weeks after all this, so we'll take a sensor with us and should map the world, or at least make a start with that. So yeah. And then after, once we get back, we've mapped the world and come back to Cambridge, we would like to reach a wider audience here. So first of all, to ensure that our data has some kind of impact, we are talking to the City Council and South Cambridge District Council, or individuals involved with that. And we will be presenting the results that we have and see how the kind of data can be useful. We're also trying to reach out to more people who are involved with setting up this kind of initiative, presenting at a Cambridge Wireless event. In addition to that, to match with the children's workshop, what we'd like to do is ensure to inspire young people to do science, because it's really cool and it's really fun, which is what we've been experiencing. So we're participating at the Center of Computer History in the Women in Computing Festival and talking to 13, 14-year-olds about what we've done and how they could do the same. And then finally, to ensure that we don't just reach people who are already interested, we'd like to explore additional avenues to advertise our project, for instance, like University Green Lines newsletter for anyone who's environmentally conscious, or anything else that we can come up with, really. And then looking further ahead, so that's the coming few months or so, we'd like to improve our prototype further. So we have been working on Megaphone as well and trying to make the power supply independent of batteries so that the user has minimal hassle. So that's one of the things we like to do, and just also generally try and make it better in lots of different ways and more user friendly. And then in addition to that, we're currently writing documentation, which to us really means very thorough manuals on how to do this so that anyone anywhere in the world at any stage can order the off-the-shelf components that we've used on purpose, plug them in and start measuring. And also to explain why we've made the choices that we have in case anyone wants to set up a similar citizen science initiative so that they don't have to make the mistakes we did. So that's in process currently, and it will be a wiki-like format, so it should be accessible and understandable for everyone. Now, I think with that, that's all that we wanted to say to you today, other than there are a lot of people who've helped us along the way, and some of them are even here, and we're really happy with that. So a thank you to all of them, to our volunteers, and to you for listening. So if you have any questions, we'd love to hear them. And if the team wants to come for questions, that might be nice.
Sure.
Yes.
Excellent presentations. I've got a question which is fundamental to the whole sensor team there, really. What are the backgrounds of each person, just very briefly? Which departments, where do you all come from? And how have you all, so what's each person's contribution? We've heard the contributions, but what different partners of university or PhDs, or what's your background?
We're all doing this MRes year, kind of just CDT and Sensor Technologies and Applications. So 1 year MS, 3 year PhD. It's our final project. That's where we came from.
Sorry, physics and astrophysics. Engineering. Physics.
Biochemistry. Engineering.
Medical physicist.
Physics and math.
Doing polymer chemistry.
Lots of them.
Lots of physics.
Yeah, I mean, that's the power of this whole thing. It's that collection of different people there as well.
Does that answer the question?
The only other question I had was about any thoughts about commercializing this, or any potential to get any IP on it?
Well, I think because we're using off-the-shelf components and we do want it to be open source and open access, that would not be a good model initially, but we can see.
Well, we did think about having the data being kind of proprietary and maybe commercializing it somewhere. City Council could be interested in good quality data.
I mean, in terms of commercialization, I think the technology is good. Getting the city council to pay for it is going to be actually nice. So that's. But I think the technology is good. I almost think it's just the application. That you have to take it to other applications where they are ways to pay for it. Because at the moment, you're asking people to pay for bad news. You need to split it so they're paying for the good news, so that they can then do a return on investment calculation. So that's just a kind of comment. I mean, you did mention advertising and product. I picked up on that. So that means that it's not a fair question, but basically you don't have a plan on how to, because for this to be sustainable, it has to make some money somewhere, because that pays for salaries. Do you have any thoughts on how it could become sustainable through a revenue stream?
My thought is to offer this to companies like Zedify to get a greener image. So, for example, if we put it on not only bikes, maybe buses, delivery cars, something, companies could work on their image to become a green company, because they accept this threat of particulate matter in the air, and they become open to it. They share their data. I think it's a good incentive for companies.
I think I would say, well, we have to talk about this more, obviously, because right now we've mainly been focused on getting it working, and we had a budget for the project that we've been using. But obviously, if we want, the sensors will start to age, and after 6 months or so, we will need to consider whether we want to replace them or just say we've mapped Cambridge and we're happy. And for that, we need more money. I would say, for instance, this is not a for-profit initiative, also because we're asking people to use the sensor and collect the data. And so it's really a collaborative effort with the community. I wouldn't say that, for instance, asking them to pay for it for the sensor would be helpful, but we'll have to look. Yeah.
So I've got a couple of questions, and part of it's related to the last. So I'm going to tell Bhupen that we make robotics, air, land, maritime robots. Would you be interested, or could this sensor be used at a much higher level, for example, mounted on drones to collect air pollution data at a much higher altitude? And so that's question one. Related, what can you do in terms of size, miniaturization, and what are the speed limits of your sensor? You know, is there a range of speed that the sensor works optimally at? Apologies, I've got 3 questions, not one.
So starting first with drones, I don't see why not. So it has an air fan and an inlet. It's just that if I don't know quite what wind speeds are like at higher altitudes, or whether that, if it's blown directly into the sensor, whether that would affect it. We haven't tried.
In fact, the batteries we're using are drone batteries,
Okay.
because the battery market for slim batteries is drone based. Yeah. So there's nothing that would stop us from putting these on drones.
I would say that the main limitation is the size and maybe weight also, because the particulate matter is quite light, but for a drone it might be too heavy. And we are looking also currently at another version of the particulate matter sensor. It's smaller, so that could be an option also to consider.
So how heavy is the box total?
I could give you this. It's without the battery, but you get a feel for the.
See, that would fit. I'd say that would fit in our routine code. And we've just opened up what we call the on-visual line of sight corridor between the cells and Cranfield. So we'll be routinely flying. Fantastic. Thank you.
Concerning the speed, like at the beginning we had the inlet facing like exactly the wind, like facing the direction of travel, and that was a problem because when wind gets directly into the sensor, that can be a problem. But then we ended up having a tube, like an inlet that is kind of bent so that wind cannot go straight into the inlet. And when we do that, I think even high speeds are not problem for the sensor. So
okay, that's a much longer conversation, I suspect. Thank you. Really enjoyed the presentation.
Great presentation and really nice work. Can you make it predictive so that cyclists can avoid hotspots and make the data actionable?
That's certainly the idea. That's the vision. If we have enough data,
There was actually some criticism we earned in the last talk we gave, that we force cyclists to go through very polluted areas to collect data for us. It's kind of defeating the purpose, but at some stage we're planning to have this heat map so you can avoid these hotspots.
Yeah, if you have enough data, you aggregate it in the way that we presented. You also have enough data to have a sense of how is it like during the day, potentially different weekdays. Eventually, potentially, you could have different months, but that would require years of data. For now, we'd be very happy to have an idea about how it changes throughout the day at different places in the city and different weekdays, and make predictions about this. Validate them, of course.
Another limitation is we will distribute to 50 people, but mainly people arrive on the morning and left in the evening, so we would probably miss a huge part of the day. So after a certain time, for sure, we could probably predict for a whole day, but in the following months, I think we will have probably on the morning and evening the prediction and during the weekend.
And are those predictive algorithms quite difficult, or is that something you can do over? How difficult is that?
It's not necessarily very difficult. We can use linear models here. They work at least in what we have researched. They work reasonably well. You can also go about it in a very complicated way. Train a neural network and do all sorts of kind of sophisticated things. But you don't necessarily have to. We are keen to experiment with different approaches, but we need some more data before we can look into it.
You may have mentioned this already, but what was the total budget, and also how did the project manage it? Project management is pretty important in a very short time. Everyone has different opinions, but what was the total budget?
So we had a total budget of £5,000, of which we spent around 4,100 now, mainly on components and a bit on pizza. So I think what we try to do is, so I'm the project manager, so I'm in charge of the overall reminding people of deadlines, like we have the presentation in so many weeks. We should try to get distribution running by now, but mainly what we have is different subgroups working together on the hardware, the outreach and the data analysis. And there is an overall goal for the team, but the subgroups for themselves decide how they want to get there. I think everyone knows best with their area of expertise how they should manage their own work.
That's very impressive. That's the time frame you've had.
This is week 10, yeah.
Sorry, have you put the Google files for the PCB then into the public domain?
What would they will be?
Because I was thinking I'm always keen about making revenue early on. So I mean that's the bit of IP that you have at the moment, is that PCB board. I mean I'd almost be tempted to set up a web shop and just sell it for £25 and see how much you get. Once you get revenue, it'll start teaching you where the market is, what's the pains. You learn a lot more through sales. When you sell something, you learn an awful lot. When you give something for free, you don't get the same, people don't really value it. So I'd be quite keen for you to try selling it. You're obviously good at websites and stuff, and I should try it.
What we want to do is, because not everyone has access to a PCB milling machine or is comfortable with ordering components from your own app to make it happen. What we do want to have is a kit for distribution, put everything in there, send it to people, and suppose we could have a margin on that.
Absolutely, make sure it's 75%.
But also, we do think that it's very interesting. Whenever we talk to people, especially more in the maker community, they have great ideas for how they could improve the thing. And we also think that that's something that's very valuable, and that's also a form of citizen science that's of interest. So we wouldn't want to have an entirely locked in final version of our system.
Well, I know we have a business model which is quite open, isn't it? But yeah, they're still sort of profitable. So you can still have this hybrid model of something you sell and something that's quite open.
Well, I think for the average citizen, if it's a PCB plug and play, as we were talking about, that's something that you can assemble yourself and you can learn the process, and that's really fun. But that's probably as much as you can ask for someone who doesn't have electronic experience without organizing dedicated workshops. So we do think that we will end up distributing packs of components, and maybe not for free, because that's not sustainable for us.
There's a company, I think you've done very well. I've been working for about a year and a half on an air pollution device for the home. So what you've done in 3 months is really excellent. You might want to look at, there's a company who's done a similar thing in New York. It's called Airbeam, and that's where I first started looking at sensors, and their focus is on same thing, citizen science and educating and going to schools. And theirs, I think it's essentially a 3D printed casing that they use. It's very cheap. So you may want to look, and you may be able to combine your data with theirs, or they may be interested in doing work with you. I think the guy's Michael Heimbinder. Very, very nice, and it may give you some advice. I think you've done really, really well. I think the only thing with the data that I would maybe add is a time parameter to it, because especially for predictive. So if you've got the time, then you'll know that it's between 6 and 7.
Absolutely. Yeah.
So that
couldn't agree more. It's simply that we don't have enough data right now. So
I wondered if you could make one for pedestrians, whether that would cover, because they'd be going at not just during the day as well, so they might be able to combine a pedestrian. You could make the model a little smaller, or just easy to carry, and then you maybe get
more data, the back end and pedestrian.
So if we could make it into a variable, that would be fantastic. Right now, it's supposed to be for a pedestrian to wear it.
I'm wondering if legislation will come in play. You know, if you're asking people to work on the streets which are inclusive environments, and you know, we're not allowed to smoke in the workplace because obviously it injures your health. So I'm wondering if a product like this has a future, because legislation will insist that people are monitored and kind of speculate dust smell and stuff like that. But people who are actually on the street working, you're monitoring their environment, and if you're not, then you can't predict whether you're going to cause long-term effects or not. I'm just wondering if legislation might kick in on something like this. Speculative.
If you think mayors trying to create green streets, that fits right into the avenue of what they're trying to achieve in London. So by 2023, they want 80% of London to be using public transport or walking. So they're regenerating most of London with the idea of reducing pollution by encouraging cars off the road. So this would very much help the likes of the large cities to focus where the congestion areas are. But then my thoughts is, what's the good outcome? So it's maybe not a question to answer now, but think as part of this is, what could you help cities think differently and see how they operate differently? As much as, is it reducing traffic on the roads to reduce pollution? But my interest is in water and water recycling. Very much less traffic on the road, less pollution in the environment. That benefits everybody. So maybe that's also the thing as you develop this, is what's the bigger picture? How's that going to contribute to the council? That will help you sell the vision, rather than the product is great, the work you've done is brilliant. Now it's work out what's the bigger vision. How does that help cities? Because that's what will get council interested.
I would think actually add that implicitly we are also collecting traffic data, because we can see how quickly people time as well. And what we do notice is that streets where you get stuck behind cars more quickly because there's no separate bicycle lanes, that really shows up in our data. So obviously we don't have quantities now to really start seeing whether we can identify roads that are problems areas in that regard. So where bikes have to slow down and where they're experiencing high pollution because they get stuck behind cars. But that was one thing that we thought we could look at. And then also, you know, once we have the data and get people interested in looking at it, maybe it will also suggest ideas to us more. Because right now, we still don't quite know what it will look like and what kind of coverage we will have. We'll see. I will see.
We do have a meeting with the City Council in October. We present results and they might consider them for the new air quality strategy.
I think, yeah, we can also. They might not necessarily know what they want from us and from our data and how it could be helpful, but it would be, I think over the coming months, we also want to continue talking to residents and people involved in decision making to see what is actually really on their mind when it comes to air and road quality. To see how we can focus more towards that. Yeah.
So I met Francesca a week ago and I was very impressed with this. I've been involved with a project which monitored radiation in the same way and had a box about the same size. And I was certainly tempted to buy one of these. The cost then was about $400 and so on. So I think there's a hobby market here for people who, particularly in the cycling community. What is the cost of this? If you were to build in a margin.
If we can, how much does it cost us?
So the components themselves cost, we try to cut it at £50, everything together. So we could sell it for 99.
£200. But it's a fraction of the cost of the bike, isn't it? I mean, I think
absolutely. And you know, I mean, I love the idea of monitoring the bumpy roads. I mean, that I would be excited just to see what that did on a, you know, on a daily basis.
Yeah, I think studies the comments and the calls for commercialization. But at the moment, can you reassure me that you took all the bits for the open source community code and
that you are indeed putting everything back also in the open source community, and that anybody around the world can re-spin this project.
There's a GitHub repository that I update frequently, the documentation, so you can build your own. Yeah.
I think you guys need an excuse for a project in a sense, and found a great project. So I find that the amount of information there is in the open source community and interest and wizardry there is sort of helps to overcome sort of some problems we have in society with pollutions, when we can bring people all around the world to create a code for a library, and although young designers and other hobbyists to code on a microprocessor and to be able to interface with sensors, and that these sensors also become none of their code is proprietary, so that everything becomes cheap and other manufacturers can make the same product. Then there's just I'm a big advocate for the open source development, because I think this brings a lot. So indeed, I'm very glad that this can be done as much through the open source model.
I think definitely also because we're asking for a lot of people, whether that's makers to collect data. This is an open source project, but obviously, if citizens want us to continue to provide the sensors to them, because they don't feel like they can laser cut a box themselves, or they can't get all the components ready, then we need funding to make that happen.
Yeah, because that can be done sometimes. Some people make money through the open source model. Not everyone has a manufacturing facility, so some people that have got a home 3D printer sometimes will offer their services. Say, hey, I print plastic at so much per kilo, and there's often some money to be made through the manufacturing, because even though the ideas and the files can be open source, the manufacturing, you may need somebody with skills to use the machine and do that. So there is always a bit of money to be scrounged around with open source anyway.
So the idea of open source, coming back to the measurement, we really wanted to be plug and play on people's lab sensors, because in the end it's a sensor hub, and we chose to focus on air pollution and accelerometer data, but you could also as well add a radiation sensor if you want to, or some people could add, and all this data could be correlated later on. So it would be very interesting if people had new things to measure. But yeah, I think the idea of business model was more like the distribution of skills for people that just want to mount one in their bikes and not build them.
We ever thought about energy harvesting? What is vibration? You've got obviously a very clever Cambridge style 8 barrel, which does this vibration energy, I think, which is a bolder sensor before. I mean, you can generate a lot of energy to power members' devices and things. I mean, maybe it doesn't need that much energy. You probably don't even need the battery then. I know that's a higher tech version, but that would be great.
Yeah. I was saying it could be the next iteration. The most power hungry thing in that hub is the particulate matter sensor. It drains about 100 milliamps of current. And so a vibration harvesting method would, I don't think, in any way power it on its own. So, I mean, there are other ways you can have like a solar panel charging a battery throughout the day. There's also the idea of using magnets or a dynamo in the same sense, where you can put it on a bike like this and charge while you're cycling, or power the whole device while you're cycling. There's lots of risks we can take, but it's something more for the future rather than for now.
I would also say that some of those power solutions will be more expensive than others. Currently, this is £50, but that doesn't include anything that might add on to that. So we might also just offer different versions, as Lorraine was saying. If the idea is that it's modular, so you could say if someone is happy to keep changing batteries, but they don't want to spend the extra cost of solar cells, then we don't do that. Someone else might want to, and they pay a bit more, and they plug that in themselves.
So the couple we were experimenting with this induction charging mechanism in parallel all the time. We came to the conclusion, that's why we put it as a second priority, that it would double the cost easily, because these wheels with the inductive charger inside
are expensive.
very expensive. Magnets are expensive. There's companies that only do that and sell their devices for almost 100 quid.
Yeah. I mean, going down the solar cell route, that might be not that expensive. I think a solar cell in itself is like a couple of pounds, and then having relevant circuitry for it. We don't know yet if that'll be sufficient to charge an entire device for the day, a day's worth of ride. Yeah, a lot more work has to go into it.
What do electric bikes use to power their
Motorized electric bikes. As in, it's just like a massive battery which they plug at home and then put it on the bike. As in, it would be effectively the same thing as this.
Could you not tandem onto electric bikes?
That's an option.
I think electric bikes, the batteries would be an overkill for our seats.
Yeah.
Because it would not add much to put it in an electric bike. Yeah.
It's obviously, and also not everyone has an electric bike, so if you want to make this as accessible as possible, then we can't build our entire device based on the idea that someone will have an electric bike. But for someone who does, who potentially wants to build the circuit themselves to make that happen, they would be very welcome.
The USB connection to the electric.
Yeah.
Potentially.
I promise I'm not going to ask any more questions, but obviously put on the market, which you've already suggested, and let the market tell you what it wants in terms of power and stuff. You'll soon find the inquiries coming in. Can you do this? Can you do that? Agglomerate them and bring them together and determine your route map that way. That's bottom-up product development, not top-down. Top-down is when you're thinking about it yourselves. Bottom-up is when the market's telling you what it wants. Someone was just get your kit on the web store and let people from China, the US start making inquiries, tell you the direction. Go with it. It's just another strategy.
How do you consider using mobile phones for a lot of different
Yeah, so we did actually make an Android app, and Peter used it when he cycled to Paris. At that time, we did not have a reliable transmission. So we used the mobile phone to transmit all the data. And the idea was that it would use Bluetooth to interface with the sensor app, and it would simply use the data via these phones, the user subscription with the mobile phone. So you wouldn't have to think about having a LoRa module or Sigfox. In that way, it would simplify the sensor hub and would be cheaper. But you would have the hassle of connecting to it all the time, draining your mobile phone. But it is certainly something we have considered. It's very tempting to pursue that for areas that don't have a very good LoRaWAN implementation. There are some cities that don't have stations. Cambridge is quite well covered, but it doesn't go with any other city necessarily. So the phone would be more local implementation.
I guess it will be in the documentation as well.
Yeah.
So you could choose which version it is.
I have another question. The calibration of the moon ocean station. Would you be able to recalibrate or sort of compensate and say, well, actually this unit needs to be adjusted, and so that a particular sensor unit would read much more closely to one which has got a near accuracy, and sort of compensate and recalibrate all the sensors that would be able to do that?
It can potentially do it because like the values we got are always about half the year one.
Okay.
So you could potentially multiply by 2.
and gather everyone. But yeah, it's sometimes when it needs, we'll read out by that much to be tweaked. Because I noticed that, and indeed I understand that you want to have sort of qualitative relative to itself measurement, but usually if you want to have sort of measurement, regulated and measured in ways so you can compensate for any inaccuracies. These PM10 sensors, so they are commercially available modules. Other manufacturers doing so things might change obviously.
When you think it's cheating, I know I was going to ask that question. It's not cheating, just times by 2. Sensor manufacturers do this all the time. You know, my reference sensor, my sensor is an offset. You just compensate all the time. And that's most people's sensors do that.
You might even get a recommendation from like Transport for London or something of what sensor should be in there to say recommend one that they would like the accuracy.
Yeah.
Can I just add to this? I did some testing of against a dust check, and what I noticed is that depending on the kind of pollution it is, so you'll get wood burning or cigarette or car, it varies. So it's the kind of molecules that you're and the gravity of them. So the calibration, you'd have to multiply by a different factor for different kinds of pollution. So I think some of them base it on Texas dust molecule size and conditions. So it doesn't seem that easy actually to have one for all different kinds of pollution. It seems that it may fit and predict or count certain pollutions well, but then certain other kinds not so well. So yeah.
When diesel gets diesel money.
What we did find is that in the internal study, it makes assumptions about the kind of particle that's measuring the density. So even if we calibrate it exactly at, this was the Montague Road station, as soon as you move to an environment where the particulate matter distribution and the composition is different, and the calibration is off. And we don't, with this sensor, have a way of measuring what kind of particles they are. There's really just 2 outputs. There's PM2.5 is this, PM10 is this. So we can estimate, but then we don't, as soon as we start doing that, I would still be hesitant to say that that's a good estimation of the quantitative value. Because air pollution is a very sensitive topic, and there are regulatory standards that should be met. Our sensor is not fit for trying to compare to those. So I would also not want to present the data in a way that overstates how reliable it is quantitatively.
You're on a road though, aren't you? I mean, you're on a, if you take this forward, you're only on version 1. So with time you will get better. So you can't solve all the problems in the next 3 months. I mean, you can have a long-term goal, which is to get more accurate. It's fine where you are today, I get the point.
If there are no more questions, I think we'd like to thank you all very much for coming. Very interesting questions.
Thanks for the feedback.
Yeah, thank you.
Once you get to the pizza.